So I'm very pleased to introduce Stephon Alexander. So Stephon is a very versatile theoretical physicist who's worked on a wide range of things. But it turns out that in his spare time or his other life, he's also a jazz saxophonist. And he's managed to combine those two things recently in a book, which has had very favorable reviews all around. So I encourage people to have a look at the book later. And he's basically going to talk on that subject. I should point out he's a professor at Brown University, but I should also point out for the older people in the audience, they may remember Stephon from his frequent visits to UBC. And I kind of looked this up. It's actually slightly more than 20 years ago, which is a little frightening because it doesn't seem like that long. But he was a frequent summer visitor to UBC, so people will remember him around the halls of the Hennings building and so on. But it's fantastic to invite Stephon back. I'm sorry it can't be in person, to talk to us about the combination of physics and music. Stephon, it's all yours.
Hey, thank you, Douglas, and thank you. I'm now gonna, before I continue talking, it's good for me to maybe put up my slide. So I'm now gonna go and screen share. And I guess people let me know if I'm doing the right thing here. So bear with me for a second so I can pull up my, my talk, and then I will begin. So yeah, it's a pleasure. And let me say that this is an especially special talk for me. I mean, yes, I wish I could be there in person because I have warm memories of spending a lot of my time doing my PhD when I was a PhD student at Brown University, because my PhD advisor, Robert Brandenberger, would spend semesters at a time at UBC. I would come out to be with him out there and work on my dissertation. In fact, my very first physics talk ever was at UBC, and actually Bill Unruh was in the audience. And like I have all these great memories, of just interacting with many of the faculty when I was a student. And let me say that, when I think about graduate schools that, when I just think about my experience at UBC when I was this, crazy graduate student with long dreadlocks walking around the hallways and drinking coffee and hanging out with the professors and other grad students in the coffee room. It was a very welcoming place for me. I mean, I really felt welcomed by you all. And I want to say it had a big impact because it was one of the few places when I was a physics student and, just thinking back into my experience as an African-American, UBC physics was really one of those places that was very welcoming, very friendly, and that, took me seriously as a physicist, as a young emerging physicist. I don't want to go off on the names of all the professors out there that really, taught me physics and really made me feel welcome. So I want to thank you all at UBC, and I hope that you guys continue that tradition of inclusivity, regardless of who comes through your halls. And I want to just share that with you that, yes, it was 20 years ago, but I remember those days very vividly. I remember escaping to Kitsilano Beach to work on my dissertation, going on the long hikes and ending up in some random beaches whose name I won't mention, but just to say that, I heard that, just nice little walks in the beaches, Anyway, so this is especially a great time to be giving this talk, even though we are all, separated by miles. I look forward to the day when I can come out once more and, hang out in Gastown. Okay, so let's begin. So the kind of goal of this talk is to, it's mainly to have a little bit of fun, okay? I mean, yes, I'm gonna talk about the ways in which physics and music interact in my life, in my career, and both as a musician and as a physicist. But I kind of want to go through it more in a narrative form and sort of like in the spirit of Richard Feynman, the belief that storytelling, you can have lots of interesting and complicated information embedded in the stories. And so let's just begin. Much of this you will find in my book, The Jazz of Physics. Be on the lookout for my upcoming book in the next couple of months, The title of that book is called Fear of a Black Universe. It's not directly about race. It's about the dark things in the universe and the dark ideas and thoughts that we dream about sometimes about the universe that can sometimes get us in trouble or sometimes be right and wrong or wrong for the right reasons. So let me just move on. This begins with, this is not a picture of me, by the way. Well, actually, it is a picture of me. Actually, it's a picture of me. Okay. That's my saxophone. Yeah, I would say that when I grew up in New York City. I grew up in the Bronx, New York. And the neighborhood I grew up in was a very vibrant, colorful neighborhood, but it was a tough neighborhood. I grew up, in the Northeast Bronx, son of a cab driver. My mother was a nurse. And it was in the 80s. And at that time, as a teenager, not a teenager, I was probably 13 or 14 years old. I knew that I was a very inquisitive child, a young person. I used to look out at the stars at night, even though you really couldn't see the stars as clearly, because of the light pollution in New York City. And I used to wonder about what's out there, and like a lot of kids. But even though I maybe had dreamt of like becoming a scientist, scientists were not at that time. I didn't see many scientists that looked like me or from my socioeconomic background. There were many Black scientists that I saw at that age in the Bronx. But musicians were plentiful in New York City. And I came also from a musical family. And so, but throughout my teen years, it was a kind of thing where, well, there was, the usual social pressure or even how you identify yourself. And so it was much easier for me to think about being a musician. And of course, coming from a musical family, being exposed to music and being exposed to musical training at a younger age, than to be a scientist. But I definitely had that conflict as to whether I should, I could be a scientist or I should just take the path of being a musician. And in about sometime in the mid '80s, this rapper came on the scene. Now we know him in the world of hip hop music. I think it's uncontested by many people in the rap world, including people like Eminem, that this person is one of the greatest, if not the greatest rapper in history. His name is Rakim. And he rose to immediate international acclaim because his delivery was very, he was also trained as a jazz musician. So a lot of his cadence and all that stuff really was influenced by jazz music. But the content of his raps made allusions to scientific ideas. And you see, I want you to understand, like, for young people in the Bronx and in New York City, when you have the most popular person now making allusions to science, all of a sudden, what was deemed for nerds is now the cool thing. And so here's a little line from Rakim called My Melody. You can look it up online. And it says, that's what I'm saying. I drop science like a scientist. My melodies are code the very next episode. Has a mic off in the store and ready to explode. I keep the mic at Fahrenheit, freeze MCs to make them colder. The listener system is kicking like solar. It wasn't necessarily that the science he was talking about was correct, but the fact that the content and the allusions that he was making in his rap wasn't about being a thug or about being a tough guy or about being cool or about being whatever. It's about, he's talking about, the way he's going to defeat his opponents in a rap contest is to hone the energy of the star. And then, so again, this was the fact that he was making allusions made science cooler to me, made it more that, here's somebody a musician that's making it okay. And that was an influence on me. Another influence was Albert Einstein. Through this, I'm talking about influences. Like, the question is, what got me, what gave me this sort of bimodal life as a musician and a scientist? What made these worlds coexist for me, and sort of inspired me to continue along that dual path. The other person was Albert Einstein. Many of us know that Einstein what makes Einstein such a hero for many of us is that he represents, at least in the scientific world, the very best, the most excellent, the very best in terms of his groundbreaking discoveries. But Albert Einstein also struck us as, a very human person. He played the violin. When he would get stuck on problems, according to his wife, Elsa, he would improvise on a piano until something came to him. So when we think about Einstein, we also think about a personality as well as just somebody locked in a room somewhere, nerding out on a bunch of equations. And I think for me, it was important to see such an exemplar in the scientific world that it's okay to be human and have a personality, have your own personality, not fit into a particular social mold or pigeonhole, and still be maybe not like Einstein, but also be a good scientist. And another inspiration to me was John Coltrane, who by many is known to be, one of the greatest just musicians of the last century. This is a survey was done by many musicians, classical musicians, jazz musicians, rock musicians, and many of them said John Coltrane was one of the greatest musicians, period, of last century. What made Coltrane interesting, though, is not only was he known to just be able to solo through the most complicated chord changes in jazz music and make some of the most beautiful and intricate compositions in jazz, and also, but that Coltrane was also a big science buff. I discovered in writing my book, through interviewing various people that knew Coltrane, that he was hooked on Albert Einstein's ideas, and anything he can get his hands on about Einstein, he would read it. What we're looking at here is a diagram that concerns my book, where it's a hand-drawn diagram about that Albert Einstein drew. It was given as a birthday present to his friend Yusuf Latif, who was a composer. And what you're looking at, and at the end of my book, I basically show that this diagram was Coltrane was trying to figure out, by using the principles of invariance that he learned from Albert Einstein, he was trying to apply this principle of invariance to music. And we'll get back to that if there's time. We'll get back to that idea later on in the book and in my talk. So these are some of the main inspirations, and they continue to be inspirations to me. In other words, musicians and scientists who at the peak of their accomplishments managed to have and engage in a more serious way with the sciences and with the arts. But I don't want to make this sound like it was like some kind of walk in the park for me. There were challenges. So we all know that trying to forge a career as a scientist and trying to make it, all the way from doing your PhD to getting a postdoc and then getting a faculty job, then getting tenure and all these things, there are pressures out there. And I want to also say another inspiration to me was actually Professor Bill Unruh. When I was at UBC, I would sit into one of the classes that he was so passionate about teaching. It was his class that he developed on sound, acoustics, and physics. And in fact, that really inspired me. So I want to just say that, similar things happened to me. I had my own challenges, and in terms of trying to navigate my career especially as a physicist. So when I went off to Imperial College in London, that was a time when things started getting very tough, and the opportunities for me to really, this was in the year 2000. I finished my PhD in 2000. I went off to London at Imperial College, and interesting set of events started to unfold where the opportunity to actually just fully become go on and become a professional musician and do that started to look a lot more attractive than doing string theory calculations and trying to do things there. It was also a time when I was trying to merge ideas on cosmic inflation with string theory, and I wasn't getting anywhere. But I did become friends with this with this musician. His name was Brian Nino, and Brian made it clear to me. He said, "Listen, if you want to go on the road and just do music, I'll fully support that." He said, "However, you might want to, I think being a scientist is much cooler. I said, really? Well, certainly not as lucrative, I'll tell you that for sure. These are the various people that Brian produced: David Bowie, U2 to name a few, Roxy Music. He's done it all. But interestingly enough, it was actually that friendship with Brian. Most days on my way to Imperial College, I would cross his studio and hang out with him a little bit. And one day I saw him playing what I thought to be a very crazy video game and thought he was losing it. And to the left, you're seeing these little blue blocks with white blocks, and you see these little patterns. Well, Brian was playing with, he wasn't losing it. He was playing with a kind of math, called Cellular Automata, which basically, you probably heard about The Game of Life by Conway. Even Stephen Wolfram is playing with these kind of things. Not that, anyway, I'll refrain. But the point here is that these are very simple rules. And with these simple rules, you can generate a lot of complexity. And so to the right, you're seeing artwork that is created by these simple rules. This is probably called generative art. And Brian Eno put out this project called 77 million paintings, which are all these paintings that are just generated by these simple rules coming from Cellular Automata. And what the lesson there for me was, here we have an artist like Brian Eno and a musician who actually has very little or no training in mathematics and in the sciences, but he boldly was able to just jump in the math and the science and just take ideas and inspiration. And in other words, he was just merging freely without self-judgment maybe, or even pressure from his colleagues, music, the mathematics and science into his art and his music. This was nothing new to him. He did this many times with generative music, with programming FM synthesizers. There's a whole chapter in my book where I entitled Brian Eno, the Sound Cosmologist, and I talk about some of these ideas that I picked up from Brian. But the basic point there was just the fact that I was being inspired by this musician in the following way. If I asked myself if it was okay for Brian, an artist at the highest level, to boldly take ideas from science and use that to inform his art, well, why can't I do the same? Why do I have to have my world of music and my life as a musician, even my life as well, not just the ideas, but my lifestyle? At that time in London, I was going out to the jazz clubs at night. And that during the daytime, I would walk into the office as if nothing happened. And I had those two worlds very separate. Brian, amongst other musicians, inspired me that it's okay, to embrace both sides of myself and have them speak to each other in whatever way that's useful to me. That I was going to embrace that. I was going to import my music life and musical ideas into my science. Well, what does that look like? So for the rest of my talk, again, there are lots of examples. And since I wrote my book in 2015, I've continued doing more things. I've played interesting concerts, interesting musicians, so I'm just going to talk about some, with the little bit of time we have left, I'll probably spell out maybe 2 ideas. So in the interest of time, let's just talk about those things. But what I want to now do is kind of say the 2 core things that I want you to walk away with in terms of conceptual things is the importance of analogy making, the importance of analogy, okay? And having the right analogy as a paradigm for creativity, both in the arts and in the sciences. What do I mean by this? I don't want to get into cognitive science. Douglas Hofstadter wrote an entire book on this, about sort of even at the heart of cognition is our ability to make analogies and expand those analogies and specify them even more. I don't want to get into that, but what I will say is that oftentimes I find that when I work on an unknown problem of unknowns in a scientific problem, if I find the right analogy, in other words, if I find something that I understand really well that may not have anything to do with the system under study, and I start maybe comparing that analogy to the unknown, that helps me open up doors that I ordinarily would not have seen. And we'll get, I think with these examples, things that will become clearer. The other thing, I think, core principle aside from analogy making is the importance of play, the importance of improvisation. Improvisation not as something that's structured necessarily. It may be informed by structure, but the importance of playing with things, playing with ideas, playing with the math, without necessarily caring if you are immediately right or wrong. And of course, what I'm going to say is that these things apply both to music and to the activity of engaging in scientific research. And actually, there's a third, and then the key thing one of the key principles, core ideas, if you want to say, what is a common language that exists both between music, acoustic sound, and physics? Okay? In other words, is there something at the heart of both of these disciplines from which you can understand a plethora of phenomenon? And the answer is yes, waves. I know one of you we're gonna actually give that as a result, as an answer. But I gave a similar talk at Google headquarters in front of a whole bunch of engineers, and I said to the engineers, in my humble opinion, one of the most important concepts in all of science is the FourWay idea, or the FourWay Transform. And I now want to just walk through this, especially with the students and if there are people in the public, to say that this idea, there's a lot of beautiful mathematics behind it, but you can understand it by simply understanding to the left of this picture, of this slide, and to the right. You can understand much of the FourWay Transform by understanding, let's focus in on to the left. And the key concept here is whether or not waves can add up constructively or in phase, meaning that if I add waves together, the resultant waves will be larger, right? Or if I add waves that are out of phase, in the case of below in A. So in A, we have a case where we have two identical waves that are in phase, meaning that they perfectly overlap with each other. And when I add them, I get a resultant wave here where the amplitude or the height of that wave is doubled. And in the case here, when I have two waves that are actually identical in shape and height, but they're out of phase, in that what's positive here is negative here at the bottom, and what's negative is positive. And when I add those waves, you get a flat line, or you get a straight line. You get a zero wave. Okay. Now, the important thing here is that these waves are what we call perfectly periodic waves. Okay. And I want you to now think about these waves as your basic alphabet imagine that there's a language called waveology. And waveology, you can have very complex waves and complicated waves and verbs of waves and syntax of waves and all this stuff, right? But then you can have an alphabet, and the alphabet, the building blocks of waveology will be these perfectly periodic waves. And waves of different wiggles will correspond to a different letter, okay? So the idea here is that I can create, if you look at B, I can get more interesting. I can add up the basic alphabet. You see, I have one big wave here that's perfectly periodic. I have another wave with a lot more wiggles that's perfectly periodic. And I can think of all the different periodicities or undulations of these waves as different alphabets in the language of waveology. And when I add all those waves up together, based on the concept of constructive and destructive interference, I can get a complicated wave. So this is the basic idea of the Fourier idea, which is I can take simple waves of different frequencies or undulations or wiggles, all the same word, and add them together to get complicated looking waves. But the idea is way more powerful than that, because that's why our friends at SETI would want to try to find alien life forms, or by looking at very complicated signals from outer space, because they can use the Fourier idea to do the opposite. You can do the inverse, what we call the inverse, which is I can present you a complicated wave, and decompose it into simpler waves. In other words, I can do translation. I can have some language here that I don't understand, which is waveology, and I could decompose it into my basic alphabet. This is at the heart of what your computer is doing, what your cell phone is doing when it's taking a signal from a cell phone tower to, this is at the heart of how instruments work. And I'm now going to explain how much of what's going on in our universe works. But you all know this. You've all known this since you were children, listening to instruments or having your mother or your father sing to you. And so what we want to show you here is that to the upper right-hand corner, if you look at a flute, or this is an idealized flute, that the sound is nothing more than oscillating pressure waves of air pressure. But instruments are very special in that they will generate these periodic waves. Well, I'm of course idealizing for now. The waves are not as nice looking at this, but the basic structure of the waves, as you see, the lowest note on a flute, if I actually look here, is a wave that fills out a quarter of a wave. And then if I split that wave in half, X just means the length of the instrument. If I split that in half, it turns out I get another wave pattern. And if you were to guess that would be the octave, if this was C, for a C flute, for example, then if I cut that wave in half, I will get octave or high C. And if I split the wave in thirds, I'll get the perfect fifth. Ba, ba, right? Keep going, I'll get, the theme for 2001: A Space Odyssey. If I cut it in fourth, I get the perfect fourth in the key of C, that will be F. And if you see, this is exactly what Pythagoras discovered way back in roughly 500 BC. And these are what we call the different series in a Fourier transform. This is what we call a Fourier series. These are nothing more than these perfectly periodic waves that differ by an integer value. Now, so in other words, what I want you to take away now is that waves, which seem to be very ubiquitous, are at the heart of how instruments work, and at the heart of basically basically what I'm saying is that the notes that make up our Western scale, so-called diatonic scale, are nothing more than presentations of the Fourier series. So there's a deep link between the mathematics and the physics of waves and the musical scale that are the building block of our music, at least in the West. But it goes a little bit further than that, because this was discovered by the Pythagoreans way, way back. It was only until 2,500, 2,000 years later, roughly, that in the hunt to understand the motion of planets, Johannes Kepler, after being stuck and getting it wrong for many years, to understand the motion of planets using nested platonic solids, went back beyond Plato and realized that Plato was a disciple of Pythagoras, and realized that Pythagoras' idea was not just the spheres, but the music of the spheres. Was basically this idea that that dividing the string into these modes, right, is actually responsible for something fundamental about the universe. At least this was what the Pythagoreans believed, that the universe was some kind of manifestation of these vibrations. Of course, Johannes Kepler, when he was looking at the data of Tycho Brahe, basically, what you're seeing here is before he came up with Kepler's laws, he basically wrote down, he identified the data and basically the velocity of the planets. He had information about the velocity of the planets, and he looked at the ratios of the velocity of the planets when the velocity was highest and lowest of a planet, and was able to deduce from that the elliptical motion, and as well as the mathematical equation. So what you're looking down here for Kepler's law is Kepler's handwriting of the notes that he associated for each planet in the solar system. He was trying to map out the music of the spheres and being inspired by Pythagoras. So this quest to find links between something about the universe and about music was always kind of innate to some scientists, including Kepler, and it led him to the very first set of equations that turned out to be correct for the motion of planets. So now we want to take this into a more modern setting and play the following game and say, well, like Kepler, can we play this intuition and try to understand, or try to, go through the exercise of seeing to what degree and to what extent this analogy carries over for our universe and what it might teach us? And what we're looking at here is a computer simulation rendition of what we call a large-scale structure of the universe. For those of you that UBC, physics is plays a big role in understand the large-scale structure, especially the cosmic microwave background radiation, which I'll talk about in the next slide. So if you want to know more about this and the details, you can go to Douglas and Professor Halpern and others. There are tons of great people out there at UBC Physics that can tell you more. But let me now say a little bit about what this picture means. I'll tell you a funny story. I showed this picture once to a friend of mine who was a neuroscientist, and he thought it was neurons. Okay. Maybe he, I didn't tell that to his department chair. All right. So what we're looking at here, you see these dots here, and you're probably seeing some kind of web-like structure. And what you're looking at here, if you zoom in and continue to zoom in, what you'll see is that every bright dot here represents the collection of galaxies. Like our own Milky Way galaxy, this would be a typical spot in this, what we call cosmic web. So what we're seeing here is the large-scale structure of how galaxies and clusters of galaxies are organized across our universe. And what we're looking at here, if you look at this line, that's roughly 7 billion light years across. And if you continue to zoom in, you'll see a collection of clusters of galaxies. And we can ask one of the big questions in physics, in cosmology especially, cosmological physics, is to understand the same way our biology friends would like to understand. If I give you structure, if I understand structure, I might be able to understand function. So that's why cellular biologists study molecular structures within cells to understand maybe the function of a protein, right? Physicists are no different in this game. By looking at the large-scale structure of the universe, can we understand something about the functioning of the laws of physics and how it functioned to create the structure, to create this galaxy? And the fact that we see this web-like structure is telling us something. And let me go a little bit further and show you another picture. And this picture is a picture of the universe roughly 14 billion years in the past, or on the order of 300,000 years after the so-called Big Bang. And in this picture, you don't have this large-scale structure of galaxies. In this picture, there are no galaxies. This picture represents, I want you to think about, the universe is now filled with an ocean seething with a plasma. Basically, this is a medium of light and charged particles coupled together and basically undulating like an ocean, a highly energetic ocean of charged particles and coupled with light. And what we're seeing here is the last time the universe actually well, basically the time when the universe actually was transparent, because this was when the light actually, when hydrogen, so I want you to think now of electrons and protons, and light is scattered about these electrons and protons before it forms. And in this picture, the universe is expanding and cooling off as it expands to the point where the electrons get captured and release this light. And what we're seeing here is a moment called the cosmic microwave background radiation epoch, where we can now see not only the temperature, which has been measured and by the way predicted by the expanded universe paradigm, but we see the undulation or the waves of this plasma. Now, a plasma is nothing more than a medium that can carry pressure waves. These waves are pressure waves, but that's exactly what a sound wave is. Sound wave is basically when we have, for example, in the case where air pressure is modulating and waving and travels to us. But that's why, you know, underwater, it's not air waves and the pressure waves from air, but it's the pressure waves from the water molecules that's actually vibrating that we can hear underwater. So the universe back then, what we're looking at here are sound waves. But if you look at, and these sound waves contain energy, and these energies are actually, these undulations are actually very tiny, even though the background energy of the universe is homogeneous and high relative to the undulation. But these waves are what we know are the things. If we look at this picture, if to the left is the time when the universe was dominated by this cosmic microwave background radiation with these undulation, and if I look at a little spot, and if the universe expands as I go more to the right, we see that stars from these undulations, the hydrogen, along with something called dark matter and other things, basically collapse and grow into stars and become galaxies and the large-scale structure we see today. And we would like to understand this physics and understand, you know, I remember when I first saw this picture as a grad student, it was like 1989 or maybe 1991. It looked like gobbledygook to me. It was like, oh, if someone said, well, what's the physics of this? I have no idea. It looks like gobbledygook. It looks very chaotic at the very least. Now, but remember, we have at our disposal our friend, the Fourier idea, which tells me that if I look at a complicated wave, I could decompose it into simpler waves. So can I basically look at these undulations and maybe try to understand something about, through looking at it through the lens of waves, can I learn something about the physics of what's going on here? So this is kind of like the game that we play by using the analogy of sound waves, right, to understand something about the physics of the early universe. And let me, before I reveal the answer to you, let's step back and go a little bit further. Remember I told you that, let me just double check the time here. Oh, I have to now rush. So let me just say that if you do this for our flute, remember I told you that ideally the flute actually is not made up of just simple waves. What the flute actually has is not when I play one note on the flute, the wave on the right-hand side corresponds to how many oscillations a wave might have that the flute generates and how loud that is. And it's true that when I play the flute at a given note, the one that you hear is the highest, but because the flute is made up of material and has a shape, it will also vibrate at these other frequencies here. And so the lesson I want you to walk away with is that instruments, when they vibrate, they produce sound, but they also vibrate and produce other things. And those other things, those other vibrations will give me information about the material makeup of the flute. Well, it turns out if we do the same thing for the waves in this picture here, here's what we get. So this is the data. So to the right, we're looking similar to our instrument. We're looking at how many waves of a given size, okay, of a given oscillation size in this Fourier series of this cosmic microwave background radiation and how loud those waves are. And obviously I would like you to think more about this, but basically what we're seeing is that magically the universe at that stage seems to resemble the behavior of a type of instrument. In other words, as a body that is vibrating and it has a peak frequency that corresponds to the fundamental frequency, which corresponds to the size of the universe at that time. So the wave that fits in the universe. Also, you have these secondary and tertiary peaks, which will, if we believe this analogy, would give us information about the material makeup of the universe. The same way my analogy with the instrument goes. And now I can tell you that if you talk to Douglas Scott, Professor Scott, he will tell you that that's exactly what we do in the analysis of the data of the cosmic microwave background radiation to tell us how much photons are in the universe, how much dark matter is in the universe, how much dark energy might be in the universe. By looking at these peaks and using this analogy, we could deduce the material makeup of our universe, the energy budget. So because of time, I'll probably spend 1 minute to say something. I'm going to skip and say something about quantum mechanics.
I feel like you should feel free to take another 10 minutes or so. You lost so much time in the middle.
Okay, so I'll take another.
I want to hear more from you anyway.
Okay.
Even if nobody else does.
All right. So the basic point I want you to walk away is that, like, it's pretty, it didn't have to be the case that our early universe did function like some type of instrument, meaning that not only did it vibrate at some fundamental frequencies that gives us information of how large-scale structures form later on, but it also, by looking at the other peaks in these vibrational patterns, we can also read off and learn about the material, what the universe is made of. And so that's why we were able to even know about dark matter from the cosmic microwave background way before it was actually seen directly in galactic halos and large-scale structure. Okay, so I want to now talk a little bit about another analogy that we can make between not just music at the level of waves and acoustics and cosmology, but now let's jump into the quantum world. And I'm going to show you that in this case, this is now music at a higher level. This is improvised music. This is jazz improvisation. Now, the reason why, let me say something about that a little bit. There are lots of musical traditions that have improvisation, including classical music. But what makes jazz music special is that improvisation is at the forefront, which means that the strategies for improvisation and the logic of improvisation and the practice of improvisation has, been developed and not perfected, but there's a lot of science behind this improvisation. So it's fitting if you want to talk about improvisation in music to kind of draw from the tradition of jazz music. Or because I'm a jazz musician, I guess it's easier for me to draw from it. And in writing the book, I had the fortune of interviewing Sonny Rollins, and speaking of Sonny Rollins, the great Sonny Rollins at length. And Sonny revealed to me one of his techniques for improvisation. And I almost, my eyes almost came out of my head. I was so, what's the word? I was in such wonder at what he told me, because it reminded me of quantum mechanics. So let me walk you through this. So Richard Feynman taught us that one way to think, probably the way to think about quantum mechanics, is to look at the world of the very big and compare it to the quantum world. So to the upper right-hand corner, Feynman tells us that if we wanted to understand the motion of a ball, for example, which is a classical object made up of gazillions of atoms, and if I throw the ball from one initial position to a final position, one thing we'll know to know that this is a classical object is that the ball will trace out a trajectory from initial to final times that is a unique trajectory. You'll have one and only one trajectory. Now, it may be a complicated trajectory, if it's going up and down a hill, or if it's going, but the point is that it will have a unique trajectory. In this case, if it's a ball moving in a straight line, or it's moving in a line with subject to no forces, it will move in a straight line, and that line will be one unique line. But what Feynman taught us was actually, this is not what's going on in the quantum world. So to the right here, what Feynman tells us to do is, when we look at, say, one quantum particle, like say an electron, what the quantum electron is doing is that if the electron is to end up at some final point here, starting from this point, the electron you have to traverse all possible paths between point A and point B. In other words, if you were to just try to think about this intuitively, it's as if this one electron coexists in all possible paths at the same time as it goes from point A to point B. Now, this makes no sense. We don't see this happening in the real world, in the world of the macroscopic or in the quantum world. According to the mathematics of quantum mechanics, this is what we must do to get the right answer that we observe experimentally. And there's been no exception to this. And in fact, the processes that we calculate and we use to make contact with particle accelerators, such as the Large Hadron Colliders, must take these effects into account in order to get the right experimental results. There's one process that called the so-called Lamb shift, the gyromagnetic moment of the muon, that's been calculated with like 9, maybe now 10 decimal points accuracy, using this idea in quantum mechanics. So we know that at least the mathematics works. So the problem here is there's always been an issue in quantum mechanics, it still does exist, with how to interpret quantum mechanics. What's the right way to make sense of what we call without getting fancy and philosophical on you, the ontology? Okay, what's actually really going on with this electron when it's going from point A to point B, on top of the correct mathematical description? So now let me tell you what I learned from Sonny Rollins. So what we're looking at here, and this is, again, the power of the analogy making, okay? So what we're looking at the bottom here, well, in the middle here, there's Sonny Rollins, okay? And at the bottom, what we're seeing here is a notation of an improvised line, a line that Sonny Rollins improvised. And what we're seeing here is that there's a starting note and then there's an ending note here in this particular phrase. The other thing to take notice is that these two notes are harmonically related to each other. This is a D and this is a G. They're perfect fifths of each other. And so there's a sense in which, like, maybe there's something clever going on, not clever. And I want you to think of the following thing, that in between this improvised line, because it's being improvised, I could have chosen another sequence of notes that connected this D to this G. So Sonny Rollins told me that one of the things, I said, one of the things part of my conversation was to learn how to improvise better. I said, Sonny, I struggle. The music is happening so fast in real time. Sometimes I lose track of the chord changes. He said, oh no, you're thinking about it the wrong way. What you should do is target, to think of the note you want to end on and play through it, improvise through that. Don't worry about the notes in between. It's going to work. I said, really? He goes, yeah, try it. I tried it and it worked. So in other words, if I start on a D and I know I'm going to end up with a G, think about this as an initial and a final time position. And well, in one improvised line, I might take a different path, and that I might improvise through a different path of notes. I might choose another path. There are many different paths I can choose to improvise through, and it will still sound actually good. Now, of course, there's issue of timing and all that stuff, but try it someday. This is an idea in jazz improvisation called targeting, where you have an initial note and a final note, and you can just weave through trajectories of notes. And so this is a very interesting way of thinking maybe about what's going on quantum mechanically. Well, maybe the electron isn't going through all these paths, or maybe it's not some probability thing in the way we think about, like, uncertainty, but maybe the electron is just improvising its way from initial to final time. Again, so this is, cute. It's a cute thing, but this is a kind of game that I want to, I want you to think about as we, in this game of trying to leap from one, sort of zone, the zone of music, to the zone of physics, is that sometimes the exercise isn't really that the electron really is improvising, okay? But the exercise is in even making that leap. I find that it does expand my creativity in my physics, and also it gets me thinking about my music in a different way. So on that note, I want to encourage you all to find things that you're passionate about and try to merge those worlds. And at the very least, you'll have a lot of time on your, in these days to play with those things. And I want to thank you for your time, and maybe leave it up open for maybe some questions if there's time. Thank you so much.
Thanks. That was fantastic.